now, I assure you, and I'll hopefully explain that as we go along. So I want to say a bit about the history of the project and the aims. I think it's interesting to see how this emerged and the kind of needs that we saw, and then say a bit about how a few sort of science issues as examples of many science issues that have emerged from putting together a book about forecasting for Africa. So something about synthesis, which is sort of the new plotting conventions that are being put together, and then say where we stand, the current status, which is, of course, that we're nearly finished. So we had a field experiment in the year 2000 called JET 2000. It was funded by NERC, and we had quite short notice to put things together. And we, as kind of theoreticians coming from the university, we were looking at these evolution of these storms and planning to fly around these storms and basically to avoid them. We wanted to look at African easterly waves and the monsoon dynamics. So we had to put together our own strategy for forecasting. This is rather kind of an amateur effort, as it often is when we do these experiments. But we had Marianne Diop working with us, who was a forecaster at the Senegalese Weather Service. She'd done a PhD in Reading, subsequently and was working in Leeds. So for this experiment, she went to the forecast office in Bracknell, and she worked and supplied forecasts to us using, I think, the Horace system, if that's correct, the old software for the forecasts. As well as this, we had local discussions with forecasters in Niamey when we were there. The base is in Niamey, so it's very nice to see Ernest Afizimama here. So this is the first time we got to know each other, and we sort of iterated these forecasts between Niamey and Bracknell. And the way this worked was that Marianne would create bespoke forecasts and the kind of charts on the right and send them to us. But also we were receiving standard products from the Met Office. This chart on the left, I'm sorry it's a bad reproduction, but I've got this folder in my office full of these charts that were faxed to us. And this is the kind of thing we had faxed to the hotel. And we'd kind of lie on our beds in the hotel room and kind of try and figure out these things. But if you find it quite hard to see West Africa in this chart, it's partly because it's a bad reproduction. But it's also because there isn't much information there. I mean, these are aviation charts, but there isn't much to work with there. We're looking for African easterly waves. We're looking for synoptic structure. We're looking for something to tell us what's going on. And all we have are these patches that show us where the deep convection is. And we can see that on the satellite anyway, so it's not so useful. And there's a kind of vague line. Well, it's not vague, but there's a line there which is the ITD that was mentioned in the last talk. So we did the job, and the forecast from Marianne was good, and she used a lot of synoptic information she could get from Horace, but we couldn't see that directly. We only saw her interpretation of that. But at the end of this, having talked to the people in ACMAD and elsewhere, we kind of said somebody should write down, some guidance for forecasting. And at the time, I remember Chris Thorncroft said, he was leading the campaign, oh, we'll find all this in the Forecaster's Handbook, meaning the Met Office Forecaster's Handbook. So we had a look in that, and it doesn't say anything about West Africa. I mean, it's a great book, but it doesn't give you too much guidance on what to do in West Africa. So a short while after, the AMMA program came along, and AMMA has been an enormous program, taking up everybody's time enormously. It's one of the biggest research experiments ever conducted anywhere, and certainly the biggest on the African continent. So a big operation over this big network with a lot of aircraft and ships and a lot of people. And so for AMMA, there was an operational center set up. So it's actually one of the JET 2000 meetings we decided that the operational center should be a center for forecasting development. So that's what happened. And actually the French groups led this activity along with ACMAD. So it was ACMAD and principally with the French Met Office put together a forecasting program. So this is the AMMA Operational Center, AMMA AOC. And one of the key players in there was Zilor Mumba, who's the guy on the left, at the bottom here in the sort of yellow shirt. So this was quite a good activity for starting to do what we were suggesting is to collect information on how to forecast and try and document it. An important thing that was done is this, you'll see this acronym in other places, but they produced the WASA, or WAS-F, system for plotting. So the African forecast teams here, I think the colors of the shirts denote the different teams for their different shifts. We're using standardized diagnostics to analyze forecasts. So this is an example of one day in the AMMA campaign. So at the time, I wasn't working in this office. I was kind of using the services of this office, as were other people in the room here involved in AMMA. So we were based in the AMMA, and we were trying to do flights of the research aircraft and trying to forecast a few days ahead. So this example is one, I chose this example because Caroline Bain wrote a paper about this. So this is an African easterly wave case where there's particularly suppressed convection here over this area, and then very active convection in the west. And this is an interesting case because it was quite well forecast by the models, even a few days ahead, 5 days ahead. So these WASA charts, West African Synthetic Analysis, are an attempt to put standardized, formalized scientific symbolism onto the chart to explain the synoptic features. I'll show more of this a bit later. So I think you can hopefully see that the forecasts that are on the left-hand side, these are both WASF, so they're both forecasts, have some semblance of this split, at least, with more convection in the west, suppressed convection in the east. So following that process, everybody was quite exhausted after the AMMA field experiment. It took us time to get things together, but there was a workshop at ICTP that was funded by, we got some funding from WMO, and this is the first step. So this is the point at which you could say that 5 years ago and a bit that we actually started really writing a handbook. So we agreed the list of chapters, we agreed the authors, the lead authors, and something about the process. And I think these bullet points are, I hope they're significant. The top one for me is documentation. So it's simply writing down and collecting things that we already know, that are scattered around. Some are scattered around in the literature, but most are in fact not in the literature. The things that we know, but they're in maybe training material, which is used at the training centres all around the world, whether in the Met Office or Météo France or in Nigeria or in Niamey. And this material is spread around. People have common understanding of things, but that's not documented. So the first objective for me is documentation, but then we want to share good practice. That's part of the same thing, really. But following on from AMMA, where we did a lot of scientific research, to try and rapidly communicate this new research where appropriate into forecasting, to improve forecasting by bringing new research results, and where possible to provide tools for forecast training, so material like case studies and teaching materials that can be used for training. So a few other rules. I mean, there are quite a few rules we wrote down, but I've just picked a few that I think are salient here. And the bold text at the bottom. So we always want to describe the state of the art. So we want to describe the best way of doing things. There's a big debate about this because if you look at I spent some time working in Ghana. There's somebody from Ghana I know I talked to in the break earlier. In the sense that the forecasting office in Accra has state-of-the-art, equipment. It's very good computers, very good communications, lots of data there to work with. So we always want to describe the best use of the best possible tools. But at the same time, the second bullet is saying we have to be pragmatic and say that in Ghana, in Kumasi, where there's an airport, it has flights coming into the airport, there's a forecast office serving those flights. When I was there a few years ago, there was no computer. So the forecaster there has a very different environment. So we also want to have pragmatic approaches to forecasting that recognize that there can be very big differences in the tools available to different forecasters. And the final point is that we wanted to include, with appropriate caveats, methods which may be not quite tested. So there's lots of exciting ideas from other parts of the world out, things like intraseasonal variability. We saw the Kelvin waves in one of the previous talks. So those methods have a lot of potential. They're not absolutely tested in the scientific literature, but I think they're worth documenting because they're an opportunity. So we had a long workshop in Leeds that was 3 months long. I had sabbatical, and I made a mistake on this because this bottom left is not Leeds. This is ACMAD. I put the wrong slide on, so Leeds isn't quite as exotic as that. But you'll see a few familiar faces in these slides, I think. Marianne Diop, who's the other editor, is here in the black. And then Ben Orji. So our Nigerian friends will know Ben Orji, who's here. He's one of the top kind of forecasting training people from the Forecast Training Center in Lagos, and various other people. But this is a very small group. We had a small selection of those forecasters, the people who had been in the AMMA Operational Center in Niamey, a subset of those people came to Leeds, and then various other authors and contributors came, maybe for a week or 2 weeks at a time. Peter Knippertz was around, Andreas Fink came, Jean-Philippe Lafore, and somebody from Meteo France came for a while. And we worked very intensively on specific problems to try and resolve those. Then we had a chapter review workshop in March 2013, and this is the point where I was saying it's nearly finished. At this point, I thought it was all nearly finished. It's 18 months ago, but we are nearly there now. So now I just want to give some specific examples of things which are in the book and that hopefully will interest you. The first couple, well, the first one in particular is an example of how research from AMMA we're describing in the book and hopefully has some usefulness for forecasting. So there have been a series of papers from AMMA that I think have been quite influential. And Chris Taylor is the first author of most of those, describing how mesoscale convective systems, 1 in 8 of those, approximately, in the Sahel, are initiated on soil moisture contrasts in that region. So there's a dynamic sequence of convection in that one storm wets the surface, and then on subsequent next 2 or 3 days, there's an increased likelihood of a new storm being generated on that patchy wet and dry surface. And the physical mechanism is this kind of sketch here, where we have a hot surface, a wet surface next to it, and we get some vertical circulations which can initiate new storms. In this case, the images at the top show the published example where the contours here are the wet surface, there's 2 wet patches here, and the new storm forms right on the edge of that. It's very beautiful. And this new MCS forms on the edge of a previous one. So this is some guidance for forecasters that after one storm, if there's wet surface, then maybe we should watch out in that area for the likelihood of a new storm being generated. Some related work that Catherine Birch in Leeds did on the same case was to show that, in fact, gravity waves emerging from another storm in the south can also contribute to this process. So in the images, it's the same case, in fact. The parent storm is down here, and it's moving towards the southwest and decaying. So that's at the bottom of these images. And the new storm that we saw before is being born up here. And in fact, there was a gravity wave pushed out by that parent storm, and the waves here in the observed case of the green lines. And Catherine Birch got a model simulation which did something consistent. The new storm wasn't exactly the same place, but the point was a new storm generated in that zone where gravity waves met a soil moisture feature. So this tells us that, firstly, we should watch out for new initiations to the north of previous storms. I think forecasters in Africa knew that, but we have a physical mechanism already. But also that the preferred region for that is on the soil moisture anomalies. So this is an example of the reverse process. So through all our discussions with forecasters, it pushes us towards the priorities that we ought to be researching. So maybe this is, I shouldn't glorify this too much by calling it research, but I discovered, to my great surprise, that fog is a major issue in West African forecasting. It's particularly prevalent in the countries of the Guinea Coast zone. So I did a statistical analysis of the fog. So the maps at the top are showing the same information. I think it's something like 20 years. So the numbers show the average annual number of events of fog days. So fog is usually in the early hours, so about 3 to 6 in the morning. The squares are the same data. So I haven't actually finalized this. So I can ask the audience, actually, which format do you prefer for the book? You can decide. Do you prefer to have numbers here, which perhaps they overlap a bit? They're a bit confusing there in Ivory Coast. Or do you prefer these squares, which I can approve the format there. So who prefers numbers? Put your hands up. Who prefers squares? Oh, squares it is. Great. So I'll improve the legend and things like that. You don't need to worry about that. Excellent. Well, that's... yeah, you can't be co-authors, sorry. And at the bottom here's the seasonal cycle. So this is all new to me, certainly. I haven't seen this written down before, but it's a really strong seasonal cycle. As you'd expect, it's most prevalent, as in Caroline's slide earlier, when the surface is wet, but the monsoon's retreating, it gets quite cool. So here we are, August. Well, it's still monsoon in August, but then September, October, November, when the surface is humid. So there have been lots of challenges, and my excuse for the long delay in this project coming to completion is, in fact, it's not like writing the usual book, because in order to put a lot of material down, we've had to have long discussions and long debates, and we can only have so much time in workshops. We have to do a lot of this electronically by email. So lots of minor differences. For instance, all the time I've been taught about African easterly waves and discussed them with my academic colleagues. We talk about the jet level at 600 millibars and the surface, and the interacts as Rossby waves interacting, the baroclinic sense, Chinese-Stern theorem. We have all this kind of theoretical stuff. But a lot of the forecasters focus on the mid-levels, in between the middle of the wave at 850 millibars, because this is something like the steering level of the waves, and you get quite coherent vortices at that level. So firstly, for the purposes of diagnosing what's happening, you have neat vortices that you can diagnose in this pragmatic sense from your wind charts. If you only have wind charts, you can draw these quite easily. But also, we know from the US literature that these mesoscale vortices generated by storms may subsequently regenerate new storms on later days. And this is exactly what the West African forecasters tell us. When you see these vortices, it's a prime area for subsequent storm development. So those original charts that the AMMA AOC put together just had these academic levels, but we're looking a lot more at the mid-levels now. There's a few comments here. I think it's a very interesting comment, the second one, that forecasters don't trust numerical weather prediction for convection at all, really. It is quite poor, really, the numerical weather prediction of deep convection. But forecasters will use the numerical weather prediction for large-scale synoptic state. So I think that's a kind of a well-accepted kind of idea, and hopefully if the numerical weather prediction can get this large-scale state right, you can get the environment for convection and then forecast it. But actually, you may say this is not quite fair, and there's some evidence from AMMA cases that when the synoptic control is strong, whether that's from a strong African easterly wave or maybe some mid-latitude influence, in fact, the predictability becomes much higher and the forecasts are good. So that case I showed before, the 5-day forecast for convection from global models were broadly accurate with this east-west split. So firstly, it's not quite fair, but also there's a problem if you actually, it depends what you use from a large-scale state. A lot of forecasters are using convergence and divergence fields to forecast where convection would be. But of course, the convergence and divergence in the model are dictated by where the model thinks the convection is. So by using convergence and divergence, you're really just using the model convection anyway. So one has to treat that with a lot of caution. So there's a lot of sort of debates to be had about these, the convection forecasting, and it's a subtle argument. And the last couple of points here, I think people agree right through the tropics that there's a lack of conceptual models for synoptic systems. And we see that from the absence of any kind of synoptic structure on that aviation chart. So we want to develop those synoptic models. An example of the kind of problems that we have, here's an example from the published literature on African easterly waves and convection. So those of us who come from a mid-latitude background are very familiar that the rainfall is tightly coupled with our synoptic systems. So when people go to look at African easterly waves for the first time, they're expecting the same coupling. They ask, where is the convection related to the wave? Is it in the trough? Is it ahead of the trough? And people have been having that debate for years. Where is the convection? Well, you have to look much more statistically. The convection is much less constrained by the synoptic state over West Africa than we're used to in the latitudes. It's much more strongly controlled by diurnal cycle, topography, land surface, all those things. So this example on the right shows that. These are a lot of cases from a paper, a Fink and Reiner paper. And it shows the core, the data are basically the same, but relative to two parts of the wave. So you can look at either of these separately. And the points there are the initiations of major convective systems. So you can see the spread relative to the wave, this index point in the wave. That's the core of the vortex, basically. And the spread here, look at the scale. This is 24 degrees, basically, from here to here. So it's 2,400 kilometers. So you can't really use that synoptic map as it stands to say absolutely where the initiations are. There's some preference for certain phases of the wave, but it's really not locked in the way that convection and cold fronts are over the UK. So what we've been trying to do for easterly waves is to create a consensus of the structure. And this is something that took a lot of time, actually, in our workshops and subsequently. And the result is these nice figures, which Volker Ermert has drawn. So I can use you as guinea pigs again. And how much time do I have, Ellen? Oh, great. So I can use these guinea pigs to see if this works. But this is material that we hope can be used to teach people anywhere on easterly waves. So these plots here, the blue lines show the streamlines at the jet level, 600, 700 hectopascals. The green one is the jet, the core of the jet. And then the pink here is the preferred regions for convective initiation, based on that kind of Fink and Reiner paper. So we have preferred initiation in the trough. The trough is the tram lines, they're going north-south. And the secondary region of initiation towards the north, towards the ridge there. So that's, if I can point to it with the arrow, secondary region here. So this is the classic place to diagnose the easterly wave. It's strongest at the jet level. But then, as I was saying, at the steering level of the wave is more like halfway down, below that, 850 millibars. So here the streamlines do produce these closed centers. So we have these closed vortices. And these are probably potential vortices. And I think it's a great research project there to actually look at these vortices and see if the same ideas hold up as we see in continental USA of vortices, coherent vortices, maintaining coherence from day to day and regenerating convection. Sometimes we get vortices in the north here. The mean advection is these colored arrows here. So all the kind of moisture and humidity advection is really maximized in this layer below the jet. And then you get anomalies in total precipitable water, which are the blue and brown. So the precipitable water is low here where you get advection from desert, and high here where you get advection from south. So hopefully that makes physical sense to you. And then at the surface, well, the monsoon depth is plotted here in blue. So this is how deep the monsoon layer is. The trough is still here. The ITD now has appeared. So these are the tram lines. The heat low is this orange region. So this is where the warm air is. And the winds, this is the monsoon winds in this area. And here we've got the day plot, and the word night has just appeared here. But by night, this again comes from Caroline Bain's paper, but we see it elsewhere. We see the winds accelerating at night and the circulation around the heat low getting stronger. So we have this circulation here and stronger advection behind the trough to the east of the trough overnight in that region. So the nice thing about these graphics is that they're all in layers in Adobe Illustrator. I'm allowed to advertise a particular software. So we can combine them. So then what I did to prepare this, I just extracted all the winds from all those plots and put them on one plot. So we have the mid-level advection here in these colors, the low-level winds in black, and the jet level. And I can shift these around in different ways. So at night, we can see all this strong advection to the east of the trough. The key point here, well, I can add then the convective initiations here and the precipitable water. So the key point here is that if you look in different phases, you have different environments for convection. And particularly in this region, we have very strong shear. So the low-level wind here is almost opposed to the jet-level wind. So the black is the low-level wind, and the jet is going in the opposite direction. So we have very strong shear here, and also dry mid-levels, so which mean you get strong cold pools. These are a perfect recipe for organized squall lines, mesoscale convective systems. So that's what you get there. Whereas behind the trough, in this region, we have lots of moisture surging north, but we don't have the strong shear, and we don't have the dry mid-levels. So this convection is typically less well organized. So one aspect of this as well, in the fact that we separated out the layers here, is there's a lot of dispute between the people involved. And particularly, this is one area where the different communities, academic and forecasters, really disagreed, and it became quite heated at times. But this first one, there are two examples here. The left one is the classical. This is what you see if you do averages of European center analyses and look at a composite wave. So this is what everybody in the academic world saw. We talk to the forecasters and say, well, we never see that. We don't see it like that. It doesn't bend in this sense against the shear and the barotropic sense. And then, it's easy to see a figure that slopes this way, so we included that. But in fact, Caroline Bain showed one sloping the other way, southwest to northeast. So we're very keen also to emphasize variability in these systems. And I think, again, for future research into case studies of easterly waves is really lacking. There are very few papers of case studies. So finally, coming right back full circle, what we're trying to do is, or have been doing, and this is really an effort that the French have led marvelously, with AMMA basically working very closely with Météo France to develop scientifically based plotting conventions for synoptic features in the region. So here is what a WASA plot looks like now. I took this case from last summer when there was, in fact, a fatal airline crash, if you remember, somewhere in the Sahara here. But there are all sorts of pieces of information on here. The blue lines here show mid-level dry air, which obviously influences storms, convection in particular. We've got real data, synoptic observations here, surface pressure. So similar products are being developed by AMMA, and you can see this site, if you Google for MISVA, that's a site that the Senegalese Weather Service are developing in collaboration with the French. And I just wanted to compare where we've come then from what we had in Jet 2000 to guide our flying to what the potential activities in West Africa could use now to make it synoptic planning and decisions. So here's a list of chapters. The ones with stars are not quite finished. There's a lot of names on here and a few names in the room here. It's nice to see. It's a big effort involving a lot of people. And it's very nearly completed. I won't make too many excuses for delays. The main reason I would say is that we're all getting distracted all the time by trying to do new research on the interesting problems that come from our discussions. The next steps are completion of a few plots. Publication process will take order of a year. Translation to French is a major priority because slightly less than half West Africans are French. I know our Nigerian friends will always tell us that the majority of West Africans speak English, but the majority of countries speak French. So the translation to French is important. And then there needs to be processes to embed this material into operational practice. And I listened with interest to the possibility of a severe weather forecasting demonstration project in West Africa. And hopefully this material would be beneficial to that activity. So I can conclude there. Thank you.
Thank you. Thank you very much.